A very good morning to one and all. Today we'll be seeing the topic of integral calculus. What do we mean by integral calculus? Before going to the depth of this part, let's see what do we mean by integration. Integration, it is nothing but a process of summing up together. That is, say if there are n number of pieces, then bringing all those n number of pieces and adding them or summing them is the process of integration. In integration, we'll be seeing three different types of integrals: the line integral, the double integral or the surface integral, and the triple integral or the volume integral. What is a line integral is, if the process of integration is done along a curve or over a path, then we treat it as a line integral. If the same process of integration is done in two dimensions, that is over a region, then we call it as a double integral or surface integral. If the process of integration is done in three dimensions by taking or considering the length, breadth as well as the height, that is in space, then we call it as a volume integral or triple integral. So before going to today we'll be seeing what is a line integral. Under line integral, we'll be covering two types of line integrals. The first one is the scalar line integral and the second one is the vector line integral. But before going to the scalar or vector line integrals, first let me throw a light on few basic topics regarding this. So let's start right from what do we mean by a scalar and a vector. So before going to the concept of line integral, we'll be seeing what do we mean by a scalar and a vector. So let us see in brief what do we mean by a scalar and a vector. What's a scalar function, a vector function, a scalar field, a vector field first, then we will move on to line integral. So first let's see what do we mean by a scalar or a scalar quantity. What is a scalar quantity is, a scalar is nothing but a quantity which has only magnitude, or else in specific what we can say is a scalar is represented by a number. It can be expressed as a number. Say for example, I take 2, it's a scalar quantity, or else x, when x belongs to real number, it's a scalar quantity. Or else, if we move on to the real world, say suppose we consider the temperature of this particular room, it's a scalar quantity. Or else the time we consider, it's a scalar quantity. Or the mass of a body. Or else the speed, the distance, etc. All these quantities are scalar quantities. Then what's a vector quantity? A vector is a quantity which has both magnitude as well as direction. So a vector quantity is represented not only through magnitude but also through a specific direction, we can say. Say suppose for example, if we consider a function f of x is equal to xi bar plus 2x square j bar. So this becomes a vector quantity. Say for example, if we come to the real world things, what's a vector quantity? Say the velocity of a particular particle, it's a vector quantity. The momentum, the acceleration, all these are angular velocity, all these are vector quantities. Just now we discussed about scalar quantities. We are saying temperature is a scalar quantity. But if you want to study whether the increase or the decrease of the temperature in a particular medium, that becomes a vector quantity. So to the temperature, either increasing or through decreasing, we are assigning a particular direction. So does the temperature now of a particular medium studying whether the increase or the decrease, it becomes a vector quantity. So these are briefly about a scalar quantity as well as a vector quantity. Next, let us move on to what do we mean by a scalar function and a vector function. So when we discuss about functions will be, it may be of single variable 2 variables, 3 variables, or more than 3 variables, that is n number of variables. Say, first let us see what do we mean by a scalar function. If in a particular region of the space, to each point, if we assign a scalar value or a real value, then we call that particular function as a scalar function. So what we are doing, if we assign to each particular point of our region, say closed interval AB, which is a subset of R2, a real value, then we call that particular function as a scalar function. Say for example, let us see. Suppose if we consider a scalar function of single variable, then y is equal to x squared, or else the same thing also can be written, f of x is equal to x squared, a function of a single variable where x belongs to R. If we consider, say, f of x comma y is equal to x square plus y square plus 2xy. Now observe, x and y, there are two independent variables. So we treat this as function of two variables. Say f of x, y, z is equal to x square plus 2xy, z. Where, what do you say about x, y, z? All these are the real numbers. Then this is a function of three variables, x, y, as well as z. In case if you consider your subset or subspace as an n-dimensional one, then say suppose f of x1, x2, etc. so on, xn is equal to x1, x2 square, etc. so on into xn. There are n number of independent variables. So we treat this as a function of n number of variables. So here we are looking into scalar function. Observe whether x or else y or else x, y, z or else x1, x2, etc. so on xn. All these are, they are nothing but from the real numbers. So all these functions, whatever we are saying, we say them as the scalar valued functions or else simply the scalar functions. Then what do we mean by a vector valued function or else a vector function? If to each, let us consider, say suppose C is a subspace of R2 or else say R3, or else you can take it as an n-dimensional space as just we discussed in the case of single variable, two variables, or else multi-variables or n number of variables. If to each and every point of this C, for each P belonging to C, if we assign a vector value, then we call that particular function as a vector valued function. Say for example, f of P is equal to, I say xi bar plus yj bar. Then to the real values x and y, I am assigning a specific direction with I and j components. So the function turns to be a vector function. Or else, say suppose u is equal to f of x, y, z. Or else, the same thing, I write it in terms of vector terminology, xi bar plus yj bar plus zk bar. Then I call this as a vector valued function. Or else a vector valued function in specific can also be defined as, if I take capital F as a vector valued function, this also can be defined as f1i bar plus f2j bar plus f3k bar. Then what are f1, f2, f3? f1, f2, f3, these three are the scalar valued functions, and we call them as the components of the vector valued function. We call them as. So in specific, if I write capital F bar is equal to x square I bar plus 2xj bar, then this is a vector valued function. But observe, how many variables are there? Only one variable, that is x. So this is a vector valued function of one variable, I can say. Say suppose if I write the same function f1 bar as, say suppose x square y I bar plus 2y j bar, then what? Plus 3x y k bar. Then what do you see? Observe here. There are two number of variables as you observe. Here x, y are real values. So along with this, we are assigning a specific direction to the magnitude. Thus the function becomes a vector valued function. Say suppose the same thing f2 bar is equal to, if I write xi bar plus yj bar plus zk bar. Observe, 1, 2, 3, three independent variables. So this is a vector valued function of three different variables or three independent variables. In the similar way, I can define, say, fn bar is equal to x1 I bar plus 2x2 j bar plus x3, x4, so on, xn into k bar. Observe here, how many number of variables are there? N number of variables are there. And then the function is expressed as a vector valued function. x1, 2x2, x3, x4, so on, xn. These are the component functions as we are saying as f1, f2, f3. So this is example of a vector valued function with n number of variables. So that's what we mean by a scalar function as well as a vector valued function. What is the significance of these two functions? That is the scalar function and the vector function. What is their major role? The major role is they define the field. So we move on to what do we mean by a scalar field. What's a scalar field? If to any region, say suppose I call the region as, say, P as the region, which is a subspace of R3, three-dimensional space. If to each and every point of P, if there is a specific scalar valued function, a scalar function has a specific value, then that particular function we call it as a scalar field. We call it as. What do we mean? Suppose when I switch on the AC of this particular room, what will happen? After, say suppose 5 minutes or 10 minutes, the air or the cool breeze spreads over the entire room. So what is happening is the breeze is spreading or it is covering a specific field. That's what we mean by a scalar field. That is covering up or gearing up to a particular area is a scalar field. So what's a scalar field? In brief is for each and every point of any region in the space, if the scalar function has a specific or a particular value, then we call it as a scalar field. What are the examples of a scalar field? As we are discussing, the temperature of this particular room, it spreads all over. So that's a scalar field. Or else you take a long rod, hit it. So what will happen? You start from one end. Slowly the heat passes through the other end. And after certain instance, you can observe the heat on the other end of the rod. So what's happening? The heat or the temperature is transforming throughout the rod. That is, it is spreading its field. So that's a scalar field, what we can say. Then moving on to the next thing. After scalar field, Now let's see what do we mean by a vector field. Let us suppose, say again P is a subspace of our three-dimensional space P R3. If to each and every point of P for x, y, z belonging to P, if a vector function has or assigns a specific vector, then we call that field as a vector field. So, if P of x, y, z is equal to, say, some xi bar plus yj bar plus 2z cube k bar. This must be for all x, y, z belonging to our domain P. Then we call, if for every point we are assigning a vector function, then we call that particular field as a vector field. What is an example? Say for example, if you consider the flow of electricity or a magnetic field, you consider the velocity field. All these come under vector fields. If you place a bar magnet in front of us, and if you place some magnetic, materials of iron, etc., all those around, what do you observe is all these iron fillings, whatever you keep in front of or in the surrounding area of the bar magnet, they come and get attracted to the magnet. What is that? The place of the magnet is here itself, but its effect is in the surrounding area. That itself indicates that the effect of magnetism surrounds the area, which creates a field what we call as magnetic field, we call it as. So, magnetic field, electric field, etc., all these come under vector fields. Let us see a simple example. Say, if you switch on a light, what will happen? The electricity passes to all directions wherever you lay the cable, electric cable. But if you pour some water, say here, then what will happen? Does the water flow to all the directions? No. Wherever there is down, the water flows to the down direction. What is the difference between here and there? The flow of current is a scalar field, creating a scalar field. It passes to all directions wherever there is an electric cable laid. But when you pour a bottle of water here or on the table, the water definitely will come down only because it searches the direction where a down or the flow of water could be. So that is the simple major difference. Flow of current and flow of electricity. Current flow, it is only a scalar quantity, but electric field, it is a vector quantity. So that's the simple difference between the scalar and vector fields. So after just knowing what is meant by a scalar, a vector, scalar function, vector function, and a scalar field and a vector field, now let's move on to what do we mean by a line integral. As we discussed earlier, line integrals are of two types: scalar line integral, vector line integral. If our field is a scalar field, then we define a scalar line integral. If the field is a vector field, then comes the vector line integral. So, what is a line integral? Let us see. Let's take a curve. What is a curve? How do we define a curve? Say suppose if I denote the curve as C, then the set of all points x comma y such that x is x of t and y is y of t, that is both x and y are functions of t, a single variable where t belongs to closed interval AB, that is collection of all such points give rise to a curve. So let us suppose that this is a curve or a path, and our domain is, say, suppose closed interval AB. Now divide closed interval AB into n number of equal paths, say T0, T1, T2, T3, etc. so on. So A is equal to T0 and then T1, T2, etc. so on, Tk minus 1, Tk, etc. so on, Tn is equal to B. What does this do? It gives rise to a partition. What do we mean by a partition? Dividing the given curve into some subcurves, like, say, corresponding to this point, let us say this as P0, then P1, P2, etc. so on, say Pk, etc. so on, say Pn. What is happening? We are subdividing the given curve into subparts, where P0 to P1, we call this as the length of the arc, or else the arc length, and is denoted by delta S1. Say suppose in the interval Tk minus 1, Tk, the length of the arc, let us say as delta Sk, let us suppose. Let us suppose that we have a function. Say, if the function is a function of, it can be single variable, two variables, or else a number of variables. Say, let us suppose that we have a function of two variables, f of xy. Then what does our pk represent? This represents the point xk, comma, yk. What does that xk? This xk is nothing but a function of x of tk, and our yk is nothing but a function of y of tk. So now let us consider over each and every arc. This is another arc length. Say, observe, this is another curve, and then another length of the arc. So compute what is f of xk, yk into delta sk, the product. For each and every particular subarc, we are computing f of xk, yk into delta sk. What it is exactly, let's come back once again. So how many are there? We have n number of subarcs like this. For each and every subarc, let us compute the same product. Then sum up all those things. Summing up, summation. How many we are saying? We are saying n number of subarcs. Summation, k is equal to 1 to n, f of xk, yk, delta sk. If the limit delta sk tends to 0, sigma k runs from 1 to n, f of xk, yk into delta sk, if the limit exists, then we call the limit as the scalar line integral, or the line integral, we call it as. Then we are saying delta sk. What is this delta sk? I am saying that delta sk is nothing but the length of the arc. How would we find out the length of the arc delta xk? As we are saying, our function is a function of two variables. What is this? This is nothing but x dash t whole square plus y dash t whole square, integration from tk minus 1 to tk. Why? Because we are considering the kth subarc. So the kth subarc is in the partition tk minus 1 to tk. So the limit of integration will be from tk minus 1 to tk of dt gives the length of the subarc. So in case if the limit as delta sk tends to 0, summation k runs from 1 to n f of x tk y tk into delta sk. If it exists, then the limit is called the line integral of the function f along the curve C. Or else, if limit delta sk or else delta tk tends to 0, summation k runs from 1 to n f of x tk comma y tk delta sk we are saying. But what is delta sk? Delta sk is nothing but the length of the subarc. I denote the length of the subarc with norm. So norm delta sk of dt. If this limit exists, then that limit is called the line integral. We are saying delta sk tend to 0. What does that mean? The length of the arc should be 10 to 0. That is, the length of the arc is almost 0. When does that happen? Say, we are saying this is the length of the arc, this area. This becomes 0. When does that happen? If the point is closer, the distance is getting decreased. Point is still closer, distance is still getting decreased. Point is still closer. Observe the distance now, almost minimal. So, if the point is still closer, the distance becomes 0. So, when does the distance of the length of the arc become 0? If there are n number of points we are saying, but if n tends to infinity. That is, we divide this curve or else path we say into infinite number of points, and if we sum up all those sums, that is limit as n tends to infinity, summation n is equal to 1 to infinity f of x t comma yt into square root of the length. Length is given as x dash t whole square plus y dash t whole square of dt. If this limit exists, then we call the limit as the line integral along the curve C, and we denote it with integral f ds along the curve C. We call it as line integral of f along the curve C, we call it as. Then what is exactly the line integral we are saying? Say, let us suppose that I take this as an electric cable. I am dividing the electric cable into n number of sub-parts. Say, like this, I am dividing. So, each part will be having a specific length. What is that we are calling as our arc length, and we are saying as delta sk we are saying. So, when I switch on the, say suppose in this room power supply is there. What will happen? When I switch on the switch there, then my tube light is somewhere here, the tube light is. Then what will happen? A cable is laid from that position to this position. The electricity passes through the cable. What is that cable? That's nothing but my curve, or else the path I can say as it is. I'm dividing it into n number of parts. So, when a charge flows along this path, what is that charge? The charge is nothing but my function f of xk and yk. This is the electric charge density which is flown on each and every subarc of this. Say suppose I have a tube light at this position, a tube light at this position, a light at this position, and then how can I connect? My electricity or electric cable runs like this, and then like this, and then somewhere to like this. So what is that? This is a path. What I am doing that path? I am dividing dividing it into sub pieces are sub arcs. So these particular come as my delta Sk or else arc length for me. And the flow of electric charge density is my function. So how would I get the current flow or electric charge passing through this electric wire? That is obtained by the charge density multiplied by the density flown over that particular curve of length delta Sk. So that gives what? Only for this particular position. If I wanted to calculate on the entire path, what is the electric charge flown, then what should I do? This part I will add up, next I will add up all these. What is that addition? That is nothing but summation. K is 1 to n number of paths. And if I say if limit n tends to infinity, that is I take n or else infinite number of subarcs, then what do I get ultimately is the electric charge flown on this particular path. That's how do we generate the electric bill for a particular flat or industry, etc. so on. This is how do we measure. So what is this line integral? Here we are interpreting as is nothing but the flow of electric charge along the particular path. So this is the scalar line integral. Then what do we mean by a vector line integral? Nothing specific or much to be explained. The same thing earlier we consider a scalar field. Now we are moving on to the vector field. The same curve we will take, the curve is the same, the partition is the same, and our function is not the same. Earlier the function is a scalar point function. Now our function is a vector point function f of xk comma yk. Now earlier the length of the arc is a scalar. Now it's no more a scalar, it is now a vector. Then integral along the curve C, if we find out f of xk yk as it is a vector quantity, I am denoting it with a bar dot delta sk bar, then that gives us the vector line integral. Earlier we are saying integral f ds along the curve C. That's a scalar line integral, ordinary multiplication. Whereas now as the function is vector function and the length of the curve is also measured as a vector, so now the scalar integral is now moving on to the vector line integral. So how do in specific we define this? It is nothing but integral along the curve C. If we simply denote f as f bar dot delta sk as ds bar, then along the curve C, f bar dot ds bar gives us the vector line integral. So the only difference is if your function you are considering is a scalar function, then that gives rise to a scalar line integral, and if the function you are considering is a vector valued function with a specific direction, then the integral what we consider becomes a vector line integral. Now let's see in general mathematically how do we define this one. Say along the curve C f ds, the line integral along the curve C, in general if a function is a function of single variable, then f of x t norm xt dash of dt, then this is called the scalar line integral, and integral along the curve C f bar of xt dot norm xt dash of dt, then this is called a vector line integral. Observe, function is function of single variable. Say suppose if you have function of two variables, then what will happen? The same integral gets transformed to, instead of f of xt, xt yt into under root x dash t whole square plus y dash t whole square of dt. F function is function of two variables. Say if it is more than two variables, three variables, then what will happen? xt, yt, zt, x dash t square, y dash t whole square plus z dash t whole square of dt, or else instead of mentioning the whole thing, simply we write it as norm of x dash t of dt, we call it as. That is how we compute mathematically the line integral. Let's see how do we compute the line integral with the help of an example. Let us consider a curve. Say our curve x is, the domain is 0 to pi interval to 3-dimensional space R3. So where the curve x of t is defined as cos t, sin t and then t. Observe here, the curve x is now nothing but, if we write analytically the curve, this is nothing but set of all points of the type x, y, z, whereas our x is cos t, our y is sin t and our z is t, where what is t? It belongs to 0 to pi. It is. Then let us see, we have the function f is defined as set of all xy plus z. Then how do we compute the integral along the curve f of ds, along the curve C? What do we need? Integral along the curve C f of ds. So what we want? It is nothing but integral along the curve C f of x, y, z, norm x dash t of dt. So what is our capital X of t? It is nothing but cos t, sin t and then t. Then what is our x dash t? The derivative. Derivative of cos t minus sin t. Derivative of sin t, cos t, derivative of t, 1, all these with respect to the independent variable t. Then what is norm x dash t, that is square root of minus sin t whole square, which is sin square t plus cos t whole square, cos square t plus 1. What is this? Square root of, we know from the trigonometric results, sin square t plus cos square t is 1. So this is 1 plus 1, which is root 2. Then what is our value of the integral? Let's compute our integral. What is our function? F of x, y, z is defined as x, y plus z. So x, y plus z. So what is x? We have our representation, x is cos t. So this is cos t. What is y? Sin t. Plus what is z? T. So cos t, sin t, t. What do I do is, to make integration simple, I multiply with a 2 and divide with a 2. So this is 2 cos t sin t plus t. So what is this? This is nothing but half of 2 cos t sin t is sin 2t. So sin 2t plus t. So now let's compute our value of the integral. So this is integral along the curve C f ds is equal to integral. Remember the limits of integration are C is from 0 to 2 pi. So integral 0 to 2 pi f of our capital Xt. So that is nothing but half into 2 sin 2t plus t into norm x dash t dt. What is norm x dash t? Already we have found its value. That is root 2. So root 2 into dt. So this is nothing but integral 0 to 2 pi. As root 2 is a scalar, let's bring it out. So root 2 outside of half into sin 2t plus t of dt. Now integrate it with respect to t. So this is root t into half into integral sin t 2t, that is minus cos 2t divided by the derivative of the inner function 2t, that is which is 2, plus integral t, that is t square by 2, and between the limits 0 to 2 pi. So what is this? This is nothing but root 2 multiplied by minus 1 by 4 cos 2t plus t square by 2. Now it's time to substitute the limits of integration 0 to 2 pi. Substitute the limits. While substituting the limits, first we substitute the upper limit and then the lower limit. So the upper limit is 2 pi. So this is minus 1 by 4 cos 2 pi plus 1 by 2 t square, that is 2 pi whole square, minus, coming to the lower limit, minus 1 by 4 cos 0 plus t square, 0 square by 2. So the value is 0. So what is this? Nothing but root 2 into minus 1 by 4. The value of cos 2 pi or cos 360, it is 1. So minus 1 by 4 into 1, that is 1, plus half into 2 pi whole square, that is 4 pi square by 2. So which is 2 pi square minus, this is cos 0, the value of cos 0 is 1, minus 1 by 4, so that is plus 1 by 4 and then 0. So minus 1 by 4 plus 1 by 4 gets cancelled each other. So there remains root 2 into 2 pi square, or else 2 root 2 pi square becomes the value of the integral f ds. Now let's see how to compute a vector line integral. Earlier what we have seen is computation of a scalar line integral. Let's see how do we compute the vector line integral. Say suppose our curve is from the domain 0, 1 to R3 three-dimensional space, whereas our function f bar is given by xi bar plus yj bar plus zk bar, and our curve is xt bar is ti bar plus 3t square j bar plus 2t cube k bar. Then first let's compute what is x dash t. Then derivative of t, that is 1 into I bar, so that is I bar, plus t square derivative 2t into 3, So that is 6t j bar plus 2t cube k bar. T cube derivative 3t square into 2, 6t square of k bar. Then our function capital F bar is xi bar, so that is t I bar plus yj bar, so that is 3t square j bar plus z k bar, so that is 2t cube of k bar. Then integral along the curve C, capital F bar dot ds bar is nothing but integral along the curve C, capital F bar dot x dash t bar of dt, which is nothing but along the curve C, our F bar is ti bar plus 3t square j bar plus 2t cube k bar dot our x dash t is I bar plus 6t j bar plus 6t square k bar of dt. So which is nothing but integral. As our curve C runs from 0 to 1, the limits of integration becomes 0 to 1. Now first, before computing the value of the integral, compute the dot product. How do we compute the dot product? If a bar is a1 I bar plus a2 j bar plus a3 k bar and b bar is another vector b1 I bar plus b2 j bar plus b3 k bar, then the dot product between the two vectors a bar and b bar is defined as a1 into b1, a1 b1 plus a2 b2 plus a3 b3. Why? Because remember, I dot I is 1, I dot j, I dot k, they are zeros. Similarly, j dot j is 1, k dot k is 1, the rest all are zeros. So using that particular formula, what do we get is, this is I dot I, so 1, so this is t plus j dot j 1, 3t square 60, 3 6s 18 t cube plus k dot k 1, so 2t cube into 6t square, 2 6s 12, t cube into t square, t to the power 5 of dt. So this is integrated t integral t square by 2 plus 18 into t cube integral t to the power 4 by 4 plus 12 into t to the power 5 integral, that is t power 6 by 6 between the limits 0 to 1. Then time for the substitution of limits. Substitute the upper limit first. Upper limit is 1, so this is 1 square by 2, so that is 1 by 2 plus 1 power 4, that is 1 by 4 into 18, or else simply we can write it as 9 by 2 plus this is t to the power 6, that is 1 by 6 into 12, or else can be written as 2 minus lower limit 0 here, 0 here, 0 here, so the lower limit is 0. So which is nothing but, take LCM, 2 is LCM, this is 1 plus 9 plus 2 2's 4, so that is 1 plus 9 10 plus 4 14 by 2, which is 7. So the value of the integral along the curve C is nothing but 7, we can say. So that is how do we evaluate a vector line integral with the help of dot product.